All right, there's this Tollen's test, which is a test that is used for the presence of aldehydes in compounds. It actually, as a result of it, makes silver metal. And so if the reaction occurs, meaning there's an aldehyde present there, you will effectively reduce silver from the 1+ charge to its metallic form. And that is actually how mirrors are made. This is actually a very common thing that chemists do. They can make like Christmas tree ornaments out of things in their lab by just doing the Tollen's test. And so you have an aldehyde and you mix together in there all of the reagents of the Tollen's test, and you get a silver mirror. So here is a reaction. You have ethanol reacting with Tollen's reagent, which is really just silver 1 nitrate that is aqueous. And you react them together, you get the silver metal and ethanoic acid or acetic acid, which is what is more commonly known as vinegar. And obviously, if there is no aldehyde there, it's just not going to work. So you're left with no mirror forming. So you can know that the molecule doesn't have an aldehyde. Basically, the silver nitrate is a very weak oxidizing agent, and aldehydes are very reactive. So since it's very reactive and the oxidizing agent is weak, they will react. But if you had a ketone, which is less reactive than the aldehyde, with the weak oxidizing agent, they don't react. If you have an alcohol that's even less reactive than the ketone, same thing, it's just not going to work. Another test that's commonly used in organic labs is Benedict's test. And this is a test for vinylic alcohol and aldehyde groups, but it's more commonly used to test for the presence of sugars. Because in essence, sugars have this vinylic aldehyde and alcohol. All right, so vinylic meaning they're next to each other, they're on adjacent carbons. And that's what we see here with this 2-hydroxypropanol. In the presence of copper 2+ ions, they form copper 1+ ions, so the color changes from this pretty blue color to brick red. And as a result, you get 2-hydroxypropanoic acid. So again, just like with the Tollen's test, you get a carboxylic acid as a result. And right here we have sugars. There's D-glucose, which is basically just, let's just say it's glucose. And in here you've got the aldehyde and the adjacent hydroxyl group, the adjacent alcohol, and so they're vinylic. And you add Benedict's test to it, or the Benedict solution with that copper 2+ solution, and they will always react sugars, so you get that brick red color resulting. And again, here's your carboxylic acid produced. All right, a final type of reaction that can be done to any of these things are reductions, which are the opposite of oxidations. So organic reactions that reduce the number of carbon-oxygen bonds by either removing oxygen atoms or by converting carbonyls into alcohols. And so here we have the reduction of aldehydes and ketones. So propanol in the presence of hydrogen and a platinum catalyst. Will form 1-propanol, a primary alcohol. So this is literally the exact opposite of what we saw before with the oxidation of a primary alcohol. We had formed an aldehyde. Now we're reducing an aldehyde to make a primary alcohol. So this allows chemists flexibility. We can kind of do what we want. So if we have hydrogen and platinum catalyst, we can make the primary alcohol from an aldehyde, or if we want the aldehyde, we can take the primary alcohol, add some acid, and heat it up and get the aldehyde. All right, and then we can take the ketone, in this case acetone, again, react this one in the presence of hydrogen and the nickel catalyst. And we form the secondary alcohol, in this case 2-propanol or isopropyl alcohol. So again, it's the exact opposite of the oxidation of a secondary alcohol, which always produces a ketone. The reduction of the ketone always produces a secondary alcohol. As you might expect, there's no such thing as a tertiary ketone, because if I had a ketone with 3 groups on it, like that, the carbon right here would have 10 electrons on it, which cannot happen, and so tertiary alcohols cannot be made by reduction. Example 10, write a balanced chemical equation for the reduction of butanal. All right, so butanal, 1, 2, 3, and 4 carbons. And we need to make it an aldehyde, so there we go. Now we're going to reduce butanal using hydrogen gas in the presence of platinum as a catalyst. Just be careful, when it says hydrogen, it means H2. In the oxidation, they had H+, so that's a hydrogen ion, but hydrogen is H2. So if we're reducing this, we're going to form essentially that hydrogen there. And you know what? Let me make this blue. Okay. So now we're going to have that oxygen still there, but we're going to add a hydrogen to it, and there's going to also be a hydrogen here. So you can see the 2 hydrogens from the H2 are there and here. And this molecule that has been produced here would be, let's see, we've got carbon 1, 2, 3, 4, and there's 4 carbons. The alcohol's at position 1, so its name would be 1-butanol. So in this lecture we covered Benedict's test, which is used to test for sugars or vinylic aldehydes and alcohols, which is not common unless they're sugars. Carbonyl groups, which are the COO or CO double bond. We have dehydration, which produces water but removes water from a molecule. So that's why it's dehydration, because it's removing water from a molecule. Oxidation, where we add bonds to oxygen or add oxygen atoms to a molecule. Reduction is the opposite of that, where we are removing oxygen atoms from a molecule or reducing the number of bonds to oxygen atoms. And then Tollen's test, which is used for aldehydes.